All right, so now that we've talked a little bit about entropy and particularly the Boltzmann's equation, what we want to do is do a quick calculation. So this is going to be in your quiz, but what I want you to do is consider one of those simple systems, and in this case, calculate the number of possible configurations for 8 atoms in one vacancy. So this is related to what we did in the previous module. But then also calculate the entropy change when we introduce 10 to the 18 vacancies in 1 mole of a otherwise perfect crystal. And so then based on that, does the entropy increase or decrease? So see if you can answer these parts, and then we'll come back and work through them one by one. All right, so let's work through this entropy calculation. And we start with a system that has 8 atoms and 1 vacancy. So we start small just so we can make some comparisons to much larger systems. And so since it's so small, we could actually just draw this one, right? We could sketch it. There's 8 atoms and 1 vacancy. So that means that n, lowercase n that we talked about, right? That was the number of defects. So n equals 1. Capital N was the number of atoms, and n plus n is going to be 9, right? So there's 9 total sites. So if we just want to sketch this, we could sketch it out, right? 9 sites, and then draw 8 atoms, 1 vacancy, right? So here's an atom, keep going, and then this is my vacancy, right? So basically, we have one of these, 8 of these in this lattice, 9 site lattice, and it wants us to calculate the total number of possible configurations for this, right? So how can we rearrange these? That's what we mean by possible configurations in space with the same number of lattice sites. So basically, we're just moving this vacancy around. So I could draw another one here just to show you, right? And so we could keep doing that, and we could basically count them all up, right? So if we keep doing this, we'll get to 9, right? Because there's 9 different places that we could put the vacancy. So we know that the omega should equal 9 based on we can have it in this spot, this spot, this spot, and then all 9 spots. So that gives us 9. So let's see if our equation does the same, right? So our omega equation, if you'll recall, was n plus n factorial over n factorial, right? So this is going to be 9 factorial over 1, and then 8, right? So if you remember the reductions of this, or how we defined factorial of 9 is equal to 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? So that means that the factorial of 1 is 1. So this kind of cancels out, and then this is 9 factorial. So here, 8 factorial would be 8 times 7 times 6, etc. So basically, this is going to cancel out with this portion, and it's just going to leave us with 9. So this is equal to 9 based on our definition, right? So, but we could also just plug these into the calculator. And these are small enough values where we can directly calculate this, right? But you can imagine when we start dealing with larger and larger numbers, these calculations basically cannot be done on our sort of typical calculators. So that's why we wanted to start with a small example first. All right, so let's look at the next portion. So we wanted to look at 10 to the 18 vacancies in 1 mole of a perfect crystal. So in this one, it wants us to look at the change in entropy. So let's look at entropy configurational entropy that we had from our earlier expression, right? So we found that it was minus k times n natural log n over n plus n natural log of n over n plus n. Right? So that was our expression. So if now we have this is equal to n, and 1 mole, so 10 to the 23rd, or 6, let's write that out more, 6.022 times 10 to the 23rd is 1 mole, and this is going to be equal to n. So here, if we plug those two numbers into our expression, so this is going to be 623 times natural log of the same number over that same thing plus all right, so it just took a lot to write this out. But if we, again, this is the approximation, so we're not directly doing factorials, so we can calculate this very easily. And what we see is that this value, and when we plug this in, I forgot, sorry, this is 1.38 times 10 to the minus 23, and that was joules per mole. So when we plug all this in, we see that this value is equal to 0.0002 joules per K, or Kelvin. So it's a very small number. So one thing to keep in mind here is that so far I've calculated the entropy of our system, but in actuality, we want to get the change in entropy of our system. And so when we do that, we have to consider it against a perfect crystal. And so in that case, that value is 0. And so so basically this becomes the change because we're taking the difference of this minus 0. So that's just one thing to consider when we're doing this. We're actually after this change, but we're calculating it via this because we're comparing it to a perfect crystal, and in that case, that is just 1. So the other part of this that the question was asking, the third part, I didn't write it down here, but it was asking us if the entropy increases or decreases. And so when we're looking at this, our result here, it's a positive number. And so this implies that the entropy of our defective crystal with all of these vacancies introduced is higher than the perfect crystal by this amount. And so we see that entropy increases, right? And so that's a common thread. That's the natural order of entropy. It increases.